Hi, my name is Kevin, and I'm delighted to present our paper, Leveraging Driver, Vehicle, and Environment Interaction, Machine Learning Using Driver Monitoring Cameras to Detect Drunk Driving on Kai 23. This work was a collaboration of the Bosch IoT Lab at the University of St. Gallen and ETH Zurich, and with major support from collaborators at the LMU Munich and the University of Bern. As the title says, in this work, we evaluated the use of driver monitoring cameras to detect drunk driving. And drunk driving is indeed a major issue for road safety. Around 30 people die every day on US roads in crashes that involve drunk drivers. This in total attributes to 29% of all fatalities in US road crashes. Therefore, preventing drunk driving is a fundamental task to make the roads safer. Lawmakers see the need to act. Consequently, the US government introduced in the infrastructure bill from 2021 a mandate for the Department of Transportation to assess technologies to prevent drunk driving. However, it is an open call for solutions, meaning that scalable, low-cost, and easily accessible technologies are still needed. Our work aims to close this gap. When we look at the related work, we can learn from the prime use case, drowsiness, that is since several years available in modern cars. Around 2010, first drowsiness detection systems were introduced into new vehicles, and they used mostly thresholds for driving signals, such as the steering wheel, to alert drivers. More recently, driver monitoring cameras replaced these systems as they promise an improvement in the accuracy of detection. These cameras are used to identify eye closure times or head movements, to identify microsleep patterns, a potentially much closer estimate of sleeping behavior. Applying these learnings may help for the use case of drunk driving. In comparison to drowsiness, much less work on drunk driving detection is conducted, although studies investigated vehicle-based sensors, while others the usage of cameras. When we did our literature research, we, however, identified several shortcomings that studies did not yet address. For example, studies that use CAN data have no comparison of performance with cameras, which may work better. Or studies miss rigorousness. Many studies are not well explained or hard to follow. Moreover, many studies have participants only acting drunk without being actually intoxicated. Questionable how well a recognition will work in the real world. Or systems are just designed but not evaluated. In our work, we addressed these shortcomings by evaluating a camera-based driver monitoring system for the detection of drunk driving in a rigorous study setup. We conducted a clinical trial in a research-grade driving simulator in which we recorded the CAN bus of the simulated car and the driver with a driver monitoring camera. In total, we collected data of 30 participants. These participants drove in 3 different alcohol intoxication levels. Each of these blocks lasted 30 minutes and was always split in 3 different driving environments: rural, highway, and city. Participants started with a sober, no alcohol driving block. Then we administered them alcohol, and 2 intoxicated driving blocks followed. The first intoxicated driving block was above the globally widespread introduced World Health Organization recommended legal limit of 0.05 gram per deciliter blood alcohol concentration, whereas the second one was below this recommended legal limit. Based on this collected data, we then implemented and evaluated a machine learning system for the detection of drunk driving. I want to highlight 3 major steps in designing and evaluating the system. First, we pre-processed the data. The output were here aggregated vectors that describe the overall gaze behavior of drivers of the last 60 seconds. On these vectors, the system then classified as the second step the driver state. We have 2 classification tasks that we evaluate. We use the previous 3 intoxication levels and test different thresholds to make binary classifications. In the first task, early warning, we evaluate how well is our system capable of identifying drivers having any alcohol intoxication. In the second task, above limit, we evaluate how well is our system capable of identifying drivers that drive below and above the WHO recommended legal limit for alcohol intoxication. The actual classification was done by a logistic regression with lasso regularization. The third step was then the validation. All models were trained with a leave one subject out validation, meaning each driver was kept out once for evaluating purposes, while training was done on all remaining 29 drivers. Our result metrics are then averaged across all drivers. Hence, our performance metrics indicate how well our system works on unseen drivers. Let's take a look at the results. To identify the quality of our system, we use as the main metric the area under the receiver operating characteristic, in short, AUROC. The AUROC measures how well the model is able to separate between classes and here between the different intoxication levels that we defined. First, what we can see is that for both classification tasks, we see overall a good classification performance. For early warning, around 0.9, and for above limit, 0.8. Moreover, the performance across participants is also stable, indicated by the rather small standard deviations of the different model evaluation runs. And what we also see is that the scenarios are also rather stable, so our model generalizes quite well. Finally, we can also see that detecting any intoxication in the early warning model works slightly better than identifying the correct cutoff between an intoxication between above and below the WHO recommended legal limit. In simpler terms, it is easier to detect whether a driver drank no beer compared to 1 beer versus 3 beers. To summarize it, our system reliably detects driving under the influence of alcohol, giving us the possibility to intervene in the car. These results are not the only ones of our study. We did extensive further analysis to understand the stability and performance of our system. I want just to give you now 3 key insights that we on top found, resulting from our analysis. First, our system outperforms previous approaches based on driving data by a clear margin. Moreover, our system is highly generalizable as the detection is robust to unseen individuals, our standard evaluation, but on top also if we leave driving scenarios out and to unseen driving scenarios. And finally, our model relies upon well-known mechanisms of alcohol intoxication, like tunnel vision, as shown by explanatory analysis. My recommendation here is to read the paper for more details. To close this presentation, I would like you to give an outlook of what is next to come. Our system uses the same sensor information and features that are already today available in modern cars with their driver monitoring systems. Hence, a transfer is rather easy. But still, we recommend on the way towards the application in a real vehicle some additional evaluations just to calibrate our system for real-world usage. Our target is ultimately to design a reliable fit-to-drive warning system, so to integrate it with other use cases already implemented, and currently we conduct several studies to achieve that. If you have any questions, feel free to reach out, and thank you for watching my presentation.